Hello and welcome in a new video. And this exercise will have an application on the polar coordinates. A point M moves on a spiral polar equation given by r equal r0e theta, with theta equal omega t. It's the direction with the x-axis. So theta is the angle between OX and the position vector r, and we have r0 and omega r constants. So we have a particle m or a point m moving on this spiral. We can see that at t equals 0, the particle was at point A. Then m is moving on the spiral like this, passing through B and going in this direction. So while t is increasing, r is also increasing and theta is also increasing. Question A: what are the Cartesian coordinates of A and B? On the figure we can see that A is on the OX axis, but theta, the angle between OX and R and the position vector R, so theta is equal to 0 in this case for A. And for point B we can see that YB is not known, but XB is equal to 0, and we know that theta at point B is equal to 90 degree or pi over 2, because theta is the angle between OX and the position vector OB. So theta at point B is equal to pi over 2, and then we can find the coordinates of points A and B. The key to answer this question is to write x is equal to r cosine theta. So where is the position vector? Let's take a point M, for example here, at any instant of time t. We can write that the position vector at point M is equal to OM, and this is equal to r cosine theta I plus r sine theta j. So it's clear that x is equal to r cosine theta, and at any instant of time t, and y is equal to r sine theta at any instant of time t. So as we said, x is equal to r cosine theta, so it's r0e theta cosine theta, and y is equal to r sine theta, but r is given as r0e theta times, here we have also the expression of y, we have sine theta. So this is the expression of x and y for any point on the trajectory. Now we will consider points A and B. We have y at point A is equal to 0. So we need now to find x of A. X of A is equal to r0 e 0 cosine 0. Cosine 0 is 1, e 0 is 1, so x is equal to r0 at point A. X is equal to r0 at point A. Now for point B. For point B, we have theta equal pi over 2. So let's use these two equations to find the coordinates of point B, and taking theta equal pi over 2. So we have x b equal, we know that this is equal to 0 because theta is equal to pi over 2, and y of b is equal to r0e pi over 2 sine pi over 2. This is equal to 1, so yb is equal to r0e pi over 2, and we found the coordinates of points A and B in the Cartesian coordinate system. Now question B. Knowing that the polar unit vectors are ER and E theta, where ER, the angle between ER and E theta is pi over 2 and OM is equal to RER, calculate in terms of omega and r the radial components VR and transverse transverse component v theta and the magnitude of the velocity vector. We need to calculate the radial component Vr and the transverse or orthoradial component V theta, and finally the magnitude of V. So we can directly use the definition of Vr as R dot. So we know that R is equal to R0 e omega t. So R dot will be equal to R0 omega e omega t. And V theta is equal to R theta dot. These are the definitions of VR and V theta. Okay, theta dot is omega, in fact. So you will get the expressions of VR and V theta. And finally, we can deduce the magnitude of the velocity vector, which is equal to the radical of VR squared plus V theta squared. Then, in part C, they ask to determine the angle between V and ER. The angle between V and ER, we have two ways to see this angle. One of the ways is to use the scalar product. The scalar product of V dot ER is equal to, so this is V, R dot ER plus R theta dot E theta dot ER. So we can now develop R dot ER times ER will give R dot plus R theta dot E theta dot ER. E theta dot ER will give 0 because E theta and ER are perpendicular to each other. Okay, so we have R dot plus 0. This is from one point of view. هذا هو scalar product. We use the definition of the scalar product, the first definition. The second definition of the scalar product is equal to the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. So the magnitude of V is written like this, times the magnitude of ER, it's 1, times cosine of the angle between V and ER, we called it cosine alpha. Okay, so now we obtained a relationship between R dot, the magnitude of V, and cosine alpha. Therefore, we can find cosine alpha. It's equal to R over the magnitude of V. Or simply, we can see it as cosine alpha is equal to VR over V, the magnitude of V. This is the cosine direction. So we can immediately write cosine alpha equal to VR over the magnitude of V. Okay, so you can immediately write this equation. Okay, let's then find this cosine. So it's equal to, we need to write what is R dot. So R dot is equal to R0 omega E omega t. And you have already found the magnitude of V. And therefore we can deduce what is the angle alpha. It's pi over 4. In question D, they ask to find the radial component AR and transverse component A theta and the magnitude of the acceleration vector A. So let's write the definition of the acceleration vector in polar coordinates. So AR is equal to R double dot minus R theta dot squared. We have already calculated what is R dot. So R dot has this expression R0 omega E omega t. So R double dot will be equal to R0 omega squared E omega t. And we will keep theta dot as omega. So theta dot squared is equal to omega squared. And we will find that AR is equal to 0 in this case. And theta, A theta is equal to R theta double dot plus 2R dot theta dot. So theta double dot will be equal to 0 because it's d omega over dt and we had a constant omega. So we will find A theta. Then we can deduce the magnitude of the acceleration vector. It's equal to the radical of AR squared plus A theta squared, and it will be equal to r0 omega squared e omega t. Exercise 18. A car travels along the level curved road with a speed which is decreasing at the constant rate of 0.6 meters per second each second. The speed of the car as it passes point A is 16 meters per second. So we have a car traveling on a curved road. It passes from point M to point B at with a speed such that this speed is decreasing at the constant rate of 0.6 meters per second each second. So this expression means simply that dv over dt is dv over dt because it's the constant, it's the rate of decrease of the speed. So it's dv over dt, and since it's decreasing, so the variation should be negative, and this is equal to 0.6 meters per second each second, so it's minus 0.6 meters per second squared. We have the speed of the car at point A, it's 16 meters per second. They want us to find the magnitude of the total acceleration of the car as it passes point B. So they want us to find the acceleration at point B, which is 120 meters along the road from A. So we have AB is equal to 120 meters. And the radius of curvature at B is given as 60 meters. So they want us to find the total acceleration. So here we don't have the equation of the trajectory. We don't have the expression of the position vector, or neither the expression of the velocity vector. How can we find the acceleration? So we can simply write that the total acceleration is equal to the tangential acceleration plus the normal acceleration. Do we have the tangential acceleration? Yes, it's equal to the to dv over dt. Okay, so we have the tangential acceleration. We need to find the total acceleration. There's something missing. We need also to have the normal acceleration. What is the normal acceleration? The normal acceleration is equal to v squared over r at point B. Do we have v squared b? No, but can we find it? Yes, we can find it because we have a constant tangential acceleration. So since we have a constant tangential acceleration, we can write that vb squared minus v squared is equal to 2as, where s is the path length. We know that the path length is equal to 120 meters. We know a, so this is a tangential. Do we have VA? Yes, we have VA is equal to 16 meters per second. So we can deduce then VB. VB is equal to the radical of VA squared plus 2AS. And this will give 10.85 meters per second. Okay, so we calculated VB. We can deduce the normal acceleration is equal to v squared b over r, where r is the radius of curvature. It's also given. We can find an. Okay, we have at and we have an, then we can find the total acceleration, which is equal to the radical of at squared plus an squared. And all the units here are in the SI system. So the map to solve this exercise is to write a total is equal to, or a squared total is equal to a squared t plus a squared n. So the magnitude squared of the total acceleration is equal to a tangential squared plus a n squared. We know at squared. At is equal to minus 0.6 meters per second squared. But we don't know an. We can find an because an is simply equal to v squared over r. V squared over r. But which v? They want us to find the acceleration at point B. So here we need to find the normal acceleration at point B. But we don't have VB squared. We only know VA. From VA, can we deduce VB? Knowing that we have a constant tangential acceleration? Yes. Using this equation. Okay, it's the equation in the constant acceleration model. And therefore we found the magnitude of the acceleration vector. Let's solve now exercise 19. The motion of a particle m is described by its position vector OM in the Cartesian coordinate system. It's equal to t ex plus t squared over 2 ey plus t ez. Now we can see that the unit vector ex is the same as I, the unit vector I. Ey is similar as the same. Ey is j and ez is k. Okay, this is another representation, but it's the same. So we have a particle moving in the Cartesian coordinate system. We have the position vector. Part A, determine the speed and acceleration at point M. So we need to find the speed and acceleration. Speed and acceleration, so we need to find the magnitude of the velocity vector and the magnitude of the acceleration vector. How do we find the velocity vector? If we have the position vector, we need to make the derivation. So V can be written as Vx plus Vy plus Vz. It's equal to dom over dt. So we need to derive this expression with respect to time, and this will give us Ex plus 2t over 2 Ey plus Ez. And then we can find the magnitude of the velocity vector, which is equal to the radical of 1 squared plus t squared plus 1 squared, and this is equal to the radical of 2 plus t squared in meter per second. We need now to find the acceleration vector to deduce finally the magnitude of the acceleration vector. So the acceleration vector is equal to ax plus ay plus az. It's equal to dv over dt. So we go back to this expression and we derive this with respect to time. So we will get ey, because here we have 1, so the derivation of 1 with respect to time is 0. And also for this term, we will only have a is equal to ey, so it's 1 ey. So the magnitude of the acceleration vector is equal to 1 meter per second squared. Question B. Give the expressions of the tangential and normal components of the acceleration. So we need to find at and an. At is equal to d over dt of the magnitude of v. So we need to derive radical of 2 plus t squared with respect to time. And we need to find the normal acceleration. Let's start. So the at is equal to v dot et. This means that we need to derive the magnitude of the velocity vector with respect to time. And we have v equal radical of 2 plus t squared. We need to derive this expression with respect to time. Let's use this. Let's get use of this rule in math. So the derivative of radical of f of x with respect to x is equal to f prime of x over 2 radical of f of x. So this will give at equal. So the derivative of our function is 2 plus t squared. The derivative is it's 2t. So here there is 2 times t over 2 radical of 2 plus t squared. We have 2 in the numerator and 2 in the denominator. They will cancel each other. And then we will obtain at. How can we find an? So an can be found from two ways, using two methods. But so the first method is to write it as the radical of a squared minus at squared, and the second method is to write it as v squared over rho, but we don't have the radius of curvature, so we will not use the radius of curvature in part B. We'll keep it to part C. So an will be equal to the radical of a squared minus at squared. We have the magnitude of a squared, it's equal to 1, minus at squared, so it's the magnitude of the tangential acceleration vector, it's equal to t squared over 2 plus t squared. And so let's do the same denominator, and we will obtain an in meter per second squared. Finally, question C, deduce the expression of the radius of curvature of the trajectory. So we need to find rho. If we have an, can we deduce rho? Yes, we can. By using the equation of the normal acceleration, the formula gives an squared equal v squared over rho. So we can deduce rho equal v squared over an, and we can therefore find that rho will be equal to, so v squared is 2 plus t squared over an, which has been just found from the previous question. And we deduced rho.